I use chemistry to find new ways of making new molecules. Some of the molecules that I'm interested in making are called biaryls, and they are a set of privileged structures that are found in drugs, agricultural chemicals, and functional materials, so ones that conduct electricity or emit light. In fact, around 10% of the top 100 drugs contain this biaryl structure. For example, drugs that are used to combat cholesterol or antiretroviral drugs used to treat HIV. In addition, it's also a key component to a potent antibiotic called vancomycin, which is the last line of defense for clinical infections such as MRSA. Now, today I'd like to tell you a story about a rather esoteric chemical called benzene and how we use this to make these important biaryl structures. Now, benzene is the hyperactive cousin of a chemical you may have heard of called benzene. Benzene was first discovered over 100 years ago, but due to its highly reactive nature and the harsh conditions required to make it, scientists consider it a chemical curiosity with almost no practical uses. However, this just made it all the more interesting to work with. And eventually, chemists came up with much milder methods for generating it, and so benzene came into its prime. Now, my research is about finding new challenges for benzene, and in particular, making biaryls. What is a biaryl? Well, a biaryl is made up of two aryl units connected by a single carbon-to-carbon bond. You can see an example behind me here. An aryl is a flat ring of atoms, primarily carbon. You may have come across it before in Manchester's wonder material, graphene, which is a sheet of aryls. In this example, the large ring, or aryl at the top, is connected to the small ring, or aryl at the bottom, by the pink bond, which is a carbon-to-carbon bond. Now, the most obvious way to make a biaryl is to take the two aryls and just stick them together. However, the challenge to this lies in how chemical reactions are done in a big mixing pot, and we have to make sure that aryl A connects with aryl B, not A to A or B to B. Now, benzene is full of energy just waiting to become an aryl. All we have to do is find a suitable source of aryl B so that the two will join together in the way that we want them to. And to do this, I put a hook and an activator onto aryl B. The hook catches benzene as it is formed, and once the two pieces are joined together, the activator promotes the couple to rearrange, forming the strong carbon-carbon bond and the desired biaryl. Now, this is actually an X-ray image of one of the molecules I made using benzene. You can see what's left of the hook to the side and the activator to the bottom. At the moment, I'm looking to vary these as much as possible so that we can try to find some really interesting properties and hopefully some molecules that are really useful. I think you'll agree with me that benzene has come a long way since its humble origins, and I think it will continue to surprise us in the future. Thank you.